In the last video, we touch on the three states of matter that are really most familiar to our everyday experience: the solid, the liquid, and the gas. And I kind of hint that there is a fourth state, which I don't cover because it's usually not the domain of an introductory chemistry course, but a little bit of a discussion ensued on the message board for that video. So I thought I would at least touch on that fourth stage, and that's the plasma. And I'll do it in a suitably bright color. Plasma. And people consider it a fourth state because it has some properties of gases. In some ways, it's almost a subset of gases. But it also has properties of conductivity that you normally wouldn't associate with the gas. And what it is, and just so you know, when you first hear it, you think, oh, that's a fairly exotic thing, plasma. And in the first video, I say, oh, it only, something that occurs at high temperatures, which isn't exactly 100% right. It doesn't have to be at high temperatures. I really should have said under extenuating circumstances where you have a very strong electromagnetic field, or something has to happen to essentially bump the electrons or move the electrons off of gases that would have otherwise have kept their electrons. So it's kind of analogous to what happens in metal. When we talk about metal bonds, we talk about this notion of a sea of electrons, where, let's say if we talked about iron, what happens with most metals is that they have so many kind of electrons, and they're so willing to give them, that the electrons just kind of float outside of the atoms themselves and create this kind of big sea of electrons, and then the atoms themselves become positively charged ions because they essentially donated some electrons to the sea. So they're attracted to the sea, and that's what makes them malleable, and even more importantly, what allows them to conduct electricity. But they're all really packed closely together, and it's a very dense structure. A plasma is a situation where if you take gases, and remember, gases, things are pretty far apart. So you take a bunch of gases, and they have high kinetic energy, although they don't have to, well, it could be it could be very low pressure, but they're moving around and they're bumping into each other, but they're not close to each other. They don't have a fixed structure with each other, or they're not rubbing against each other like in the case of a liquid. But what happens in a plasma, well, one situation is that you apply such a strong electromagnetic field that the electrons want to disassociate. So let's say these electrons start bumping off of the plasma. And so even this, a solid has its own shape. A plasma will take the shape of its container like a gas, and sometimes it is described as an ionized gas. And it's described as ionized because the electrons are bumped off. And when the electrons are bumped off, the otherwise neutral atoms now have positive charges. And what this allows is essentially a conduction of electricity, because now these electrons are free to move. And you might say, oh, that sounds like a bizarre state of matter. Where does it exist? Well, probably closest to home, it exists in lightning. In lightning. And that's worthy of an entire video. But the idea is that you start having a huge potential difference between the clouds and the ground. And then because you have this huge voltage difference between the two, you have electrons that are essentially wanting to go into the ground, right? You have a buildup of electrons up here. You have a buildup of electrons up here that want to go into the ground. But they can't, because air is normally a fairly bad conductor. It's an insulator. But what happens is, because there's so much electropotential here, the electrons that are close in the molecules up here, and at least this is how I visualize it, their electrons want to escape from these clouds, because these clouds are starting to so their electrons start to want to move away in the air molecules. Whether you're talking about, the air is a mixture of oxygen and nitrogen and carbon dioxide. They start wanting to get away from the clouds. So they start disassociating and start forming like this ionized air. And eventually, at some point, this happens to such a degree that you can actually get conduction from the cloud to the ground. And that conduction is when the air is in a plasma state. So it's happening at the conduction allows extremely high temperatures and the electrons to flow all the way to the ground. The other common example that you might see something like this, or well, actually not like this, but at least a plasma state, is in stars. And that's because you have extremely strong electromagnetic fields, extremely high pressure, And in that type of an environment, once again, and this, I'm super oversimplifying it, you can get to a state where the electrons can get disassociated from things that otherwise wouldn't want to give up their electrons. So I thought I would touch on that because it's an interesting subject and it exists in the universe. It's actually, on a universal level, because stars are pretty much all plasma, it is actually the most common state of matter in the universe, although in our everyday life, we probably encounter solids, liquids, and gases a lot more. Now, one other thing I want to maybe clarify from the last video is I talk about the bonding between water molecules. And let's say we're talking in the solid state. So if I have oxygen, I have a hydrogen, and then I have some electrons here, and let's say there's another, let's say there's a hydrogen here, and an oxygen, and a hydrogen. Maybe there's an oxygen here that has a hydrogen. I'm just, whoops, I don't want to do that. So these are, and then this has a hydrogen, and then it has two electrons on two electron pairs. So I talked about the notion, and we talked about it many times before, that oxygen is so much more electronegative that it hogs the electrons. And so the oxygen side starts to have a partial negative charge, while the hydrogen side starts to have a partial positive side. Because when the hydrogen, essentially all of its electrons are hanging out close to the oxygen, hydrogen ends up just becoming like this proton that's floating out there, because we even said it doesn't even have neutrons in most cases. So it has a slightly positive charge. This one will have a positive charge. And the positive and the positive polar end of the water molecule is attracted to the negative polar end. And I called it polar bonds, but I really should have called it, it shows you my memory from high school chemistry is not ideal. I really should have called it hydrogen bonds. And hydrogen bonds, so this is a hydrogen bond, or this is a hydrogen bond. It's usually, it's just a matter of the name I use, but I just want to clarify that because that is what's typically used in your chemistry class, and I don't want to confuse you. And that is just the bond that exists from a partially positive hydrogen atom, because its electrons are hanging out near the oxygen, and a partially negative oxygen atom in the water molecule, because all of it's stolen all of these electrons from the hydrogen. You draw it like that. It's called a hydrogen bond. And hydrogen bonds tend to form between hydrogen and, well, really only a handful of super electronegative atoms, and that's nitrogen, fluorine, and oxygen. And that these are actually the three most electronegative atoms. So in the nitrogen, if you NH3, when it bonds with hydrogen, it essentially is so electronegative that you have the same situation. All the electrons hang out here, so you have a partial negative charge, partial positive on the hydrogen ends. Same thing with hydrogen fluorine. You get the same HF. You get the same type of hydrogen bonds. And so in this case, these guys would be attracted to the nitrogen part of other molecules or would form hydrogen bonds. So I just want to get that out of the way. And with that done, I think we can return to some of the ideas of the last video and actually do some problems. So in the last video, we saw that, let's take the case with water. Let me draw a good, actually, let me just state the problem first. So let's say that we have